Hi everybody, we are now still in problem set 1.1. And we are now in question 12. And I have to be honest with you, I couldn't solve this question by myself. So what I did was, well, the first part I could, it was easy, but the second part I couldn't do it by myself, so I will show you how I looked for the question, for the answer, and of course what the answer eventually is. Okay, so first of all, the part that was easy that I managed to do by myself. We have the drawing in the next page. Remember, questions 10 to 14 are based on this drawing. In page 9, and after this drawing, the round one, but we are now talking about the cube. And they ask us how many corners does a cube have in 4 dimensions. Okay, so previously what we had a vector of each corner was a vector. Okay, each corner, we had one corner in the origin, and we had, I'm talking about the previous question, about question 11, okay, where there was a 3-dimensional cube. And then we will understand what's going on in 4 dimensions. But first, let us understand 3. So in 3 dimensions cube, we have one corner and another corner, the J corner, okay? I'm sorry, this is the I. Okay, this was the origin. And this was the vector I. Okay? And which we talked about in question 11. And this one is 0, 1, 0 is the J vector. Okay? And another one was the K vector. Okay? And so on and so on. Let's take another one. For example, the I plus J, it was 1, 1, and 0. And so on, until we got to the one that was I plus J plus K. Okay, which was the farthest away from the origin. Okay, the most far from the origin. The opposite corner from the corner of the origin. Okay, so what do we have here? We have all the combinations of where we can put 0 and 1. Okay, this is one extreme combination of everything 0, and this is the opposite extreme combination of all the components are 1, and the middle ones are, they have 1 in some places and 0 in some places, and they have all the combinations. Okay, I didn't do all the combinations, but there are 16 combinations. How do we know that there are 16 combinations? Because there are I'm sorry, here there are 8 combinations. In the 3-dimensional case, we have 8 combinations. Why? Because we have each component can be in 2 states. each component has two options, either 1 or 0. Okay, here it's 0, here it's 1, here it's 0, here it's 0. So each component can be one of two things, 0 or 1. Okay, so the first component has two options, the second component has two options, the third component has two options, so it's 2 times 2 times 2. Okay, or in other words, I'm sorry you can't see what I'm writing. Okay, now you see. So in the first component, we have two options. In the second component, we have two options. In the third component, here it's component, okay? So it's 2 times 2 times 2, because this one can be 1 or 0, this one can be 1 or 0, this one can be 1 or 0, and in total we have 2 times 2 times 2 options or combinations, so it means 2 to the power of 3, okay? 2 times itself 3 times, which means equals to 8. Okay, 2 to the third power is 8. And in the same way, we have, okay, now back to this question, this was all to remember what was in question 11. Now we are back in question 12. We are talking now about the fourth dimension. This was the third dimension, so we have 3 components. Now we are talking about the fourth dimension. So in fourth dimension, now in the fourth dimension, with one corner in the origin, okay, the same. One corner would be with the first one. The first component has 1 and the rest are 0. The second component would have, you see, just like before, but with 4 components, okay? This is equivalent to I, okay? And this is equivalent to J. The 1 is in the second component and all the rest are 0. And so on. Okay, we have here I'm sorry, I meant 1 1 0 0 and so on until we reach 1 1 1 1. Okay, so how many options do we have here? We have, each component can have 2 alternatives, 2 options, either 0 or 1. So it's the first component is 2 options times the second component has 2 options times the third component. Okay, first component, second component, third component, fourth component, third component, fourth component. So each one of them can be either 0 or 1, 0 or 1, 0 or 1, 0 or 1. In total we have how many combinations? 2 to the power of 4, which means 2 multiplied by itself 4 times. So it's 2 to the power of 4, which means which equals to 16. Okay, so we have 16 corners. Each one of these is a corner. And we have 16. I couldn't write them all down, but it's 16 corners. Okay, this was the part that I could do by myself. And now the second part of the question was too hard for me, so I will show you how I found the answer. Okay, how many 3D faces, how many edges, and okay, and he explains that a corner is something like this or like this, that it's just a vector of a point, and an edge is a line from one point to the other if they are connected. So it's a line, okay? And okay, so now the first thing that I did was to look in what was once Cramster, now it's called Chegg. It's a homework help website, okay? And here is what they have written about this specific question. Question 12. The first part they said it's 16, okay, so it's the same. They explain it the same. 2 to the power of 4 is 16. And the second part of the question, they just say similarly, the total number of three-dimensional faces will be equal to 2 times 4 is 8. Okay? And okay, let me read the first part just to give you the whole picture. Let us consider the general corners A, B, C, D. Now, since each component in the corner can have either a value of 0 or some constant, the total number of combinations will be 2 to the power of 4, which is 16, equals 16. Thus, a 4-dimensional cube has 16 corners. Now, the second part of the question. Similarly, the total number of 3-dimensional faces will be equal to 2 times 4 equals 8. The cube also has 24 two-dimensional faces. The number of something, they forgot the word, can be found out by considering that there are 8 3D faces and each face contributes 4 edges. Thus, the total number of edges will be 8 multiplied by 4 equals 32. Okay, so it's the right answer, but not really explained. Okay, so next I went to the solution manual. Okay, which was, well, let me give you the solution manual in the end, because my second stop, okay, was actually Wikipedia. Okay, in Wikipedia, in the under I searched for a 4-dimensional cube and got to Hypercube. Okay, this is the article in Wikipedia, and they have a table, and the table says how many sides and how many corners, how many sides each geometric shape has. Okay, so if we have a point, it has one vertex. Vertex means a point. Okay, I'll just write it for you so you can know the words. Vertex means point. Okay, so a point has one vertex. A line has two vertices, 2 points in the edges, in the ends of it, okay, and one edge. Edge in their language means line, okay, so I'm writing edge means line. Okay, so a line has 2 points and one edge, two vertices and one edge, one line. A square has 4 points, 4 vertices, 4 edges, 4 lines, and one face. Okay, face, what they mean is a flat side. Okay, so I'm writing face equals side. This is the word in everyday language. This is the right word in geometry, but we are now talking about, we'll just want to make it clear. A cube, okay, a 3D cube, a normal cube that we can play dice, has 8 vertices, okay, 8 points, 8 corners, okay, a point in the book he calls a point a corner, okay, and so a normal cube, a 3D cube, has 8 corners, 12 edges, okay, 12 line segments, 6 faces, okay, 6 sides. We know a dice has 6 sides. It can fall on whichever of the 6 sides, and one cell. Okay, a cell is a 3D face. Okay, so, or a 3 face, what they call here. So cell is what we call a cube. Okay, a cube in our normal everyday sense of the word cube. So in the professional world they say cell. Okay, and a tesseract or a 4-dimensional cube, okay, we need this one. This is the one we are interested on. It's also called octachoron, something like this, and it has 16 vertices, okay, 16 points or 16 corners, 32 edges, okay, 32 lines, 24 two faces, okay, 24 normal faces or sides. Like the dice had 6 faces, this one has 24 faces, okay, 24 sides, flat sides, and 8 cells or 8 cubes, okay, and one hypercube, okay, which they call 4-face. Okay, so the last one I'm not writing because it's not useful for us. It would be 4-face equals hypercube. Okay, so this is up. I mean, this should be true because Wikipedia is seen by many experts, and if it wasn't true, they would fix it. So it's like it's our most it's the source that we can count on, but still we don't have an explanation here. So let's see if there is an explanation. Okay, this was just something that I found on the way of the binomial coefficient that I will soon show you. We get back to it in the book, okay, concerning this question. This is the Pascal Triangle, okay, it's here. Can you see it? There is one, and there and 1, and each each place is the sum of both of the places that are above it. Okay, so 1 plus 1 is 2. 2 plus 1 is 3. I don't know if you can see it. I will show you it very soon. This is gives us the binomial coefficients, which also, if you know, and if you don't know, it's interesting to know, gives us in combinatorics the how many options we have to choose what is called n choose k. If we have n, okay, n, I'll write it for you. Just close the window because there is a play. N choose k. Okay, what does it mean? It means if we have n options, how many of them will be k? Okay, like if we have n coins and each coin can be either heads or tails, how many will be heads or tails? Okay, so this comes in many places in mathematics, and it's we calculate it like this. We have, first of all, the notation is round parentheses, n on top and k in the bottom. Okay, this is how many attempts, how many times we try, and this is how many successful attempts. Okay, for example, if we say that heads or tails, one of them is the successful one and the other one is a failure, so how many are heads or tails, whichever we decide. For example, how many heads we get when we throw, we get k heads when we throw n coins. Okay, and how do we compute it? This equals to n, and this is not the exclamation mark. This is called factorial. Okay, so factorial means n times n minus 1 times n minus 2 all the way until times 3 times 2 times 1. Okay, for example, n factorial equals n, I'm sorry, so again, n factorial equals to n times n minus 1 times n minus 2 and so on times 3 times 2 times 1, or if you prefer, 1 times 2 times 3 times all the way up to n. Okay, for example, 5 factorial equals to 1 times 2 times 3 times 4 times 5, which equals to 120. Okay, so if you already knew it, great. If not, now you know it. So back to how much is n choose k. So n in the up part, and now in the bottom part we write k factorial times n minus k factorial. Okay, so we will get back to this in the book. I just wanted to explain, if someone never saw this, then now you have seen it. Okay, so and this also gives us the short version of multiplication. If you know the binomial coefficients, they are also useful when you have, for example, a plus b all this squared, or a plus b all this cubed. Okay, so we have more efficient ways to write it. If you want, you can look in Wikipedia. This part is not doesn't have a direct connection to the questions, so I'm just showing you that it's a really nice and illuminating pictures. But if you want, you have it in Wikipedia, including the fourth dimension, which is really cool, but you can see it later. So for now, we only need the Pascal triangle. Okay, so now back to the question. I'm not just showing you this, we need this. So I went to the solutions manual of the book. Okay, the solutions manual. And this is of the solution manual of the third version of the book. Okay, so the third edition. But not most, I don't know if most, but some of the book hasn't changed, and fortunately this part did not change. So if we take this question 12, it's the exact question that we need. Okay, the answer. Okay, so we have the solutions to the exercises, and now I'll read you the answer of number 12, which we need. A 4-dimensional cube has 2 to the power of 4, which equals 16 corners. And you remember, corners means points. And 2 times 4 equals 8 3-dimensional sides. Okay, we remember we had this. Okay, this is the 16 points, and 8 3-dimensional sides, which we called cell or cubes. Okay, it has 8 cubes. In a 4-dimensional cube, in a hypercube, we have 8 cubes. Back to the solution. And 24 2-dimensional faces. Okay, again, we had this in Wikipedia, 24 2-dimensional faces. A face we called a side, so 24 sides. And 32 1-dimensional edges. Okay, let's see if it's true in Wikipedia. 32 edges, which we called edge a line. So 32 lines. Okay. Okay, again, it's the right answer, but it doesn't explain anything. But he points us to worked example 2.4a in the book. Okay, the book is in the 3rd edition, so I looked it up in the 3rd edition. I got the 3rd edition as well, and the older edition. We learned from the 4th edition, but I looked up, this is the solution manual for the third edition, so I looked in the third edition book, and it looks the same. Fortunately, it didn't change. It's even got the same number in the worked example. Okay, so let's look at the worked example in our book, which is the same. In worked example number 2.4a. Okay, let's see. Just leaving the pages if we need to write. Okay, so we are still in question 12. Continued. So we go in the book to question to worked examples 2.4a. Okay, 2.4a in page 72. Okay, and I will not read to you all the. He gives the Pascal triangle. Okay, the Pascal triangle. We don't know matrices yet, so I'm not giving you the matrix. Okay, I will just draw here the Pascal triangle. The Pascal triangle. Let me take it from Wikipedia, so I'm not making a mistake. Okay, the Pascal triangle has one in the top, and then 1 and 1, and from there each line is the sum of the two, each new number is the sum of the two numbers that are above it. For example, here 1 plus 1 gives us 2, and the sides remain 1, 1, 1, because it's like here it's zeros. Okay, so 0 plus 1 gives us 1, 1 plus 0 gives us 1. Okay, so it doesn't have a contradiction. Okay, 1 plus 2 gives us 3. 2 plus 1 gives us 3. Okay, here we said we continue with 1 and 1. 1 plus 3 gives us 4. 3 plus 3 gives us 6. 3 plus 1 gives us 4. And here continues 1 and 1 and so on. Okay, and I'm not continuing to the next one, to the next line, because it's infinite. Okay, so, and we don't need any more than this. Even this line is not necessary for us. I'm just showing you that these are the numbers that we get, for example, in the a plus b squared, okay, to the second power. So we have 1 times a squared plus 2 times ab. Okay, this is 1 and 2, and 1 times b squared. Okay, this is 1. And the third, this line, 1, 3, 3, 1, is when we have a plus b cubed. So it 1 time a to the power of 3, or a cubed, plus 3 times a cubed b, plus 3 times ab cubed, okay, 3 and 3, plus 1 times b cubed. Okay, and the fourth line is, if we have, want to show it here, if we have a plus b to the power of 4, so we have 1 times a to the power of 4, 4 times a to the third times b, plus 6 times a squared b squared, plus 4 times ab cubed, plus 1 time b to the power of 4. Okay, so 1, 4, 6, 4, 1. Okay, and here we have 1, 4, 6, 4, 1. So you see these numbers are useful. So now just wanted to show you why it's called coefficients. Okay, because it multiplies each factor in the equations. Okay, so here this is called Pascal triangle. Pascal triangle. Okay, now what we have in the book in the second chapter, we have already matrices, but we don't know matrices yet. So I'm just showing you that he puts the Pascal triangle like to the side. Okay, so instead of this way of making it a triangle like we know, where the two where it's symmetrical. Okay, here we have a triangle that is like leans to one side. Okay, so I'm not talking about matrices because we don't know matrices yet, but I will show you the pattern, and maybe you will believe it this way, and in the end I will read to you this paragraph that will give some logical explanation. Okay, but first, how do we compute it? So we have the Pascal matrix. Okay, so it's like one. This is the Pascal triangle. The Pascal matrix is the same but in the shape of a matrix. So Pascal matrix and we have 1 1 1. Okay, can you see that the 1 1, this is the first line, this is the second line, so it's the same, the lines are the same, they are just the justification to the left gives it the shape of a matrix. 1 2 1 1 3 3 1. Okay, so I hope you can see the pattern that, okay, the pattern is important because we will use it soon. We will use the pattern again. The pattern is that if we want this number, we take 1 times the one that is above it and 1 time the one that is to the left of the one that is above it. Okay, so this one and this one gives this one. Okay, and this one and this one gives this one, and this one and this one gives this one. Okay, so each time it's the one above it and the one to the left of it gives the new member. Okay, so this is the Pascal matrix. Now he makes he calls it L because it's a lower matrix. We don't care what a lower matrix is yet. We will care in the future, but now we don't know it and we don't care. He computes a matrix that is this matrix times itself, okay? And he calls it H. H because it's hypercube. Okay, this is the part that we don't understand yet, okay? But we will understand in the future. Okay, so let me just give you, without explaining, the H matrix. Okay, which is the Pascal matrix times itself. So the H matrix or hypercube matrix, we are still in problem 12, continued. and it looks like this. It has 1 and then 1 1. I'm sorry, this was the Pascal matrix. Now it's 2 1 4 4 1 8 12 6 1. Okay, this is the hypercube matrix. And what is the pattern here? This is what he calls H. Okay, what is the pattern here? Each number is 2 times the one above it plus the one to the left of the one above it. Okay, so 4 is 2 times 1 plus 2. 6 it is 2 times 1 plus 4. 12 is 2 times 4 plus 4. Okay, so each one is 2 times the one above it plus the one left to the one above it. Okay, so this gives us, for example, when we talk about, you remember in Wikipedia when notice that we have, this talks about, this line of the hypercube matrix talks about a line segment. Why? Because it has 2 edges, 2 points, 2 vertices, and 1 edge, 1 line. This one talks about a square. Okay, why? Because it has 4 points, 4 edges. 4 points, 4 corners, 4 vertices. Here it has 4 edges or 4 lines. Okay, this column is points. This column is edges or lines. This column is what we call sides. Okay, and this one is what we called cubes. Okay, so in a square we have 4 points, 4 lines, and 1 side. Okay, it's flat. In a cube we have 8 points, okay, the 8 corners of the normal cube, 12 lines, 6 sides. Okay, we know we have in a dice, we have 6 faces of the dice, 6 sides, and 1 cube. Okay, and now if we continue the pattern, okay, we don't know about matrices, but we know about patterns. So let's look at the pattern. We have 2 times this plus 1 times this. Okay, remember, if we wanted 6, we had 2 times this and 1 times this. If we wanted 12, we had 2 times this and 1 times this. So we continue the pattern. And for example, 8 was 2 times 4 and 1 times 0. Okay, so here we will have 16 because it's 2 times 8, the one above it, and 1 times the one to the left, which is 0. Here we will have 2 times 12, 24, plus the one to the left of it, which is 8. So it's 32. 24 plus 8. 2 times 12 plus 8. Here we have 2 times 6, okay, which is 12, plus 12, which is 24. 2 times this plus this. Here we have 2 times this plus this. It's 2 plus 6, it's 8. Okay, and here we have 1. Okay, this is the hypercube column. Okay, so in a hypercube, or a 4-dimensional cube, we have 16 points, 32 lines, 24 sides, 8 cubes, 8 3D cubes in one 4D cubes. Okay, 8 3D cubes in one 4D cube, hypercube. And one hypercube. Okay, didn't write hypercube, but here it should be hypercube column. And now I will read to you the explanation finally, and I will hope it will give you more sense to it. Okay, so the last paragraph in page 73 gives us the explanation. Connect two squares to get a 3D cube. Connect two cubes to get a 4D hypercube. The cube has 8, we're talking now about a normal cube, a 3D cube, has 8 corners and 12 edges. 4 edges in each square and 4 between the squares. Okay, if we draw two squares and we connect, we have 4 between the squares. The cube has 6 faces, okay, like a dice. 1 in each square and 4 faces between the squares. This row 8, 12, 6, 1, okay, 8, 12, 6, 1 of a cube will lead to the next row 16, 32, 24, 8, 1. 16, 32, 24, 8, 1. The rule is 2 times the position plus 1 time the position to the left equals the position on the bottom. Okay, 2h ij plus h I j minus 1 equals h I plus 1j. h I plus 1j. Okay, now can you see this in 4 dimensions? Now we're talking about 4 dimensions. The hypercube has 16 corners. No problem. Okay, this is what we talked in the beginning. This was the easy part that I could do by myself. It has 12 edges from one cube, 12 from the other cube, 8 that connect corners of those cubes, total 32 edges. It has 6 faces from each separate cube and 12 more from connecting pairs of edges. Total 2 times 6 plus 12 equals 24 faces. It has 1 box from each cube and 6 more from connecting pairs of faces. Total 8 boxes. And finally, 1 hypercube. Okay, so I hope it helped you. It was the best I could do. I tried all sorts of places. You can also see in Wikipedia a rotating hypercube if it helps you. Surely it's very interesting and beautiful. I don't know if it helps. And also I wanted you to have the power to do it. For example, if you need a 5-dimensional cube, that you can do the next line easily. And okay, so now you have the power to do this. So thank you and goodbye.